please.
Well, thank you for everyone in Melbourne for inviting me to give this talk. I wish I was there in person, but unfortunately, I'm stuck in rainy Scotland this morning. But I'd like to take the opportunity to tell you about the statistical samples of AGB stars that we've been building up over the last few years, and why these are important not only for our field but for other fields. The real problem that we have with AGB stars is that most of astronomy doesn't care about us. We're contaminants for a lot of surveys, or we are part of a population that people are looking at, or we are part of a cosmic cycle of matter, or for a lot of fields, we simply don't matter to them directly at all. So AGB stars are something that act upon other fields, and what they need us to do is to quantify that action, to look at particular numbers or particular statistics to work out how our AGB stars, that are very dear to us, impact the stars, the phenomena that are very dear to them. So we can look at this from the perspective of taking an AGB star and changing a parameter. So if we model an AGB star, and in actual fact the mass loss is, say, slower than we model, maybe in metal poor stars or low mass stars or some particular class of star, what's the impact of that? Well, the star lives longer if it loses mass slower, and that means that we get more nuclear fusion on the AGB, and we get a brighter final luminosity for the AGB star. And what that means is that the core of the AGB star then grows bigger and less mass is lost to the ISM. The stellar remnant is larger. The star creates more metals, but whether they'll be released into the interstellar medium or not depends on the dredge-up processes. The stars should produce more dust, more near-infrared flux, because they're getting brighter and losing mass towards the end of their lives. And these factors have a wide range of ramifications for the rest of astrophysics. So it will lead to more supernovae taking place, so that will change the gravitational wave source background. It'll change the initial final mass function for stars, so it will change things like the planetary nebula shape and luminosity functions. That changes the feedback in galaxies and changes the galactic formation and evolution. It changes a lot of stellar abundances, and that changes galactic archaeology and how we interpret archaeological observations. It has a whole swathe of different impacts on galactic habitability in terms of the elemental abundances that are going into planets. It changes things like what goes into the interstellar medium, the dust physics, the dust chemistry. That changes things like the interstellar extinction curve, which affects cosmological foregrounds. It changes how the ISM cools, and that changes the gene's mass, it changes the IMF. It changes how the dust in a galaxy and the UV light interact, and that changes star formation rate traces. It also changes things like the AGB luminosity function, and that affects things like both distance modeling that we have for the cosmic distance ladder and how we treat stellar populations in unresolved and partially resolved galaxies. So AGB stars have indirect applications to a whole swathe of different astrophysical phenomena across the universe. What we need to do for these people working in these other fields, though, is to quantify how a typical AGB star of a given age or mass and metallicity changes and evolves through its time spent on the AGB while it's losing mass, how it gets from an AGB star into a white dwarf. And we need to understand the range of properties, the range of evolutionary paths that a star of a given age and metallicity can take, due to both observable properties like the pulsation properties and due to unobservable properties like binary companions, magnetism, rotation, etc. We can visualize this in a diagram like this. I've shown this before at different conferences, but we can see on the vertical axis the initial stellar mass, which is also a proxy, of course, for the age of the population you're looking at. On the horizontal axis, you can see metallicity. I've color-coded this diagram by the final C/O ratio that stars achieve in the Padova stellar evolution models. We can see that in red, we've got a region where carbon stars are produced. And in green, we have regions where the stars don't become carbon rich, either because they don't dredge up enough carbon at low mass, or because at high mass, we have hot bottom burning that transmutes that carbon into nitrogen and prevents the stars from becoming carbon stars. And what we can do is overlay on this diagram different galaxies. Each galaxy takes a different path through this diagram as it chemically evolves over time. Massive galaxies like the Milky Way will start out with globular clusters, which have very low metallicity, but quickly progress to high metallicities. And so that's why we see all these solar metallicity stars at lots of different masses in the Milky Way. We can compare this, to example, against stars in the Magellanic Clouds and other dwarf galaxies at lower metallicity that haven't had this constant replenishment or not as quick replenishment of metals to increase the metallicity of their ISM. And we can use these observations, say, in the Milky Way versus dwarf galaxies like Sextans A, to compare how evolution progresses differently at low metallicity. So we can use these to observe the effect of metallicity on AGB stars. And there have been a number of surveys that have been instrumental in doing this across the last few years, particularly with the Spitzer Space Telescope. Notably, the SAGE surveys in the Magellanic Clouds, Martha Boyer's dusting survey, and I'll also point to a JWST talk tomorrow. And Martha and I have also been doing lots of work in globular clusters, trying to fill out the bottom left of this diagram. And so we've had these major infrared surveys and some not so major infrared surveys looking at these simple stellar populations, or these simpler stellar populations in the Milky Way, to try and look at these homogeneously selected, homogeneously observed sets of stars across these different galaxies, across these different metallicities. What that allows us to do is to fill out this diagram in terms of initial mass and initial metallicity with large enough samples of stars that we can look at not only what the stars are doing, but the range of properties that stars exhibit at each point in this diagram. Now, there's a problem with doing this. These are all infrared observations. We're doing these in these galaxies because we know things like the distance to these galaxies. We know the reddening to these galaxies. We know a lot of the properties of these stars in these galaxies. The problem with these targets are faint. Some of them are over a megaparsec away, and that makes obtaining spectra and photometric monitoring for pulsation periods either expensive or impossible. Often we only have one single photometric survey or two or three photometric surveys that we can use to actually get information about these stars. We only can build up spectral energy distributions. That's virtually all we can do. The targets in these galaxies are crowded, and that makes it difficult to extract stars from them. Particularly if you're looking at optically obscured stars, they're swamped out by all the companions that the brighter stars that exist nearby. And because these targets are so far away, there's no way we can resolve them. There's no way we can look at the gas in these stars and see what the mass loss rates are, what the expansion velocities are. So we have very little idea about the gas in these winds. We have to make our estimates of total mass loss rate based on the dust opacity that we see in the infrared and based on the mineralogy that we expect around these stars and assumptions about how these stars lose mass and what the expansion velocities of the winds are. But the reality is we've got no idea of the dynamics of the wind in these stars. We don't know what the morphology of these stars are like. We don't know if we're looking at spherical stars to high mass loss, or perhaps stars with a disk that's aligned edge onto our line of sight. We can't trace the impact of things like photon dissociation, which may be very different in some of these galaxies where the UV light is actually very strong. We've got very little idea about the dust mineralogy and the dust chemistry around these stars, which are very much different to what we see in the solar system, what we see near the solar system, because these are stars at a tenth or a hundredth of solar metallicity. And this impacts on how accurately we can predict the mass loss rates for these stars. We have to rely on proxies and assumptions for many of the parameters that we would ideally like for these stars. If we look at what we do know about the gas mass loss rates, the gas dynamics in these metal-poor stellar populations outside the galaxy. We've got observations of effectively 10 stars, 8 in the Magellanic Clouds, 1 in the globular cluster, and 1 in the galactic halo. And what we've found here, even though the statistics are very marginal, we've got indications that the expansion velocities probably decrease with metallicity. And that's as expected, because we expect that metal-poor stars have dust-driven winds that are harder to operate. There's not as much dust in the winds, and it's more difficult to drive that from the star. However, the total mass loss that we see from stars doesn't seem to decrease significantly, at least as far as we can estimate from the statistics we have. And this suggests that the mass loss rates that we see from these metal-poor stars is actually set by the pulsations, not the dust properties in the wind, and that the dust properties in the wind, like dust driving mechanisms, set the outflow velocity rather than actually making it leave the star. Now, these are very first-order estimates of how the processes work. It's a lot more complex than that, as we've seen with these remarkable 3D models that are being produced. This slide appears not to have worked, but let me go back to try and work out what was said on it. If we look at stars in dust, if we look at what we have for an infrared spectrum, we've got observations of about 300 stars, about 200 in the Large Magellanic Cloud, thanks to the SAGE SPEC survey, and about 100 in other situations like globular clusters and the galactic halo. What we've found from these stars is that the conditions that we see in carbon stars don't seem to change that much with metallicity. And this is because carbon stars can dredge up their own carbon, they can make up their own dust. And so it's not difficult for them to form and drive a wind because of this. We do see some changes in chemistry. We see silicon carbide dropping out of the wind because there's less silicon to begin with, and we see more amorphous carbon taking over as a result. But we'd see very small changes in the carbon stars as we go to lower metallicity. And if we remember back at this diagram, when we're looking at the number of carbon stars that we see in metal-poor environments, we see carbon stars over a much wider range of masses. So these stars become a lot more important back in these metal-poor galaxies. However, if we look at oxygen-rich stars, the situation is a little more difficult. It's more difficult for these stars to drive a wind because they are reliant on the natal chemicals that they're born with. And this makes it difficult for them to create the silicates that we're used to see to drive a wind. And if we look at spectra of metal-poor AGB stars, they're producing significant quantities of dust. That dust doesn't contain silicate features. It's a complete featureless continuum. We think that the silicate's being replaced by something that looks like metallic iron, which has a very high dust opacity per unit mass and can therefore drive wind more effectively, even though it takes a longer time to form in the circumstellar environment. Now, these are the indications that we're seeing, but it's again based on a few dozen extremely low metallicity stars and a couple of hundred stars in slightly metal-poor Magellanic Clouds. So that's the picture for external galaxies. We're really doing number statistics in these galaxies and trying to work out from these numerical statistics what's going on. When we're looking at the Milky Way, we can do very different observations. We can look at resolved stellar envelopes. We can look at the morphology of stars. We can look at the chemistry of stars in great detail. We can make gas phase measurements in CO and other molecules to look at things like the gas mass loss rate and the expansion velocity. The problem is that generally we don't know the mass of the stars or the metallicity with any real degree of accuracy. That makes it difficult to put in the context of the diagram I showed before. A lot of the problems here are down to the fact that we don't know the distance to a lot of these stars, and we don't know the extinction to a lot of these stars, unless you're looking very close to the solar neighborhood. And this is because the parallaxes that we see to these stars can be wrong or missing due to movement of the photocenters as the convective cells move around the stellar surface. The these incorrect or missing parallaxes can cause a lot of problems when you try and work out the radius of the star or the luminosity of the star. And that makes it very hard to estimate things using these as proxies like mass or metallicity, or even working out the mass loss rate. This means that if we build up statistical selections of stars in the Milky Way, we're going to be suffering from significant and severe biases, Malmquist bias, Lutz-Kelker biases, etc. And this makes it very difficult for us to translate the information that we see in the Milky Way out to these external galaxies and make these kind of comparisons. Because we can't sample the entire Milky Way in the same way that we can sample the entirety of these other galaxies. And if we select source lists, it's hard to ensure that the sample is complete because we're missing sources that are either hiding behind molecular clouds or are masquerading as some other kind of star. Or it's also difficult to ensure that our large sample size sources are complete and free of contaminants. So it's very difficult to weed out all the things like post-AGB stars or YSOs from a sample of AGB stars, unless you go through star by star and look at them in detail. That means the existing observations are incredibly biased, primarily due to the sensitivity of telescopes in the past, but also due to the interests of individual observers. And these mean that the observations that we have at the moment tend to concentrate on the brightest objects, or the most interesting objects as individual observers see them, or in particular regions of the sky, for example, towards the galactic bulge, which might not be representative of the solar neighborhood, for instance. And this has led to the fact that surveys, individual surveys, can't really be combined in a homogeneous fashion. And they're limited in individual survey cases to only 100 objects or less typically, which makes it hard to properly examine multi-parameter problems like splitting up the effects of inertial mass and pulsation properties, for example, or metallicity and pulsation amplitude, for instance, and how these affect things like mass loss rate. We can visualize this by looking at models for stars and how they should lose mass. If I plot here the stellar mass in the x-axis versus the total mass that the star loses in the y-axis, I can split that up between carbon-rich and oxygen-rich stars at solar metallicity. Then we can see that red supergiants obviously dominate this graph because each red supergiant can lose up to 10 solar masses via a dusty wind. But of course, this ignores the initial mass function. If I multiply that through, then we can see the contribution per stellar mass of AGB stars. And we can see from this diagram that in a population of stars, if we set off a starburst, it's going to be stars between about 1 and 5 solar masses are really going to make dominant contribution back to the ISM through their AGB winds. And carbon stars are going to be a significant part of this. However, this assumes a flat star formation history. So if you want to look at a galaxy, you need to multiply the star formation history through to work out what the AGB stars are doing. If I do this for the Milky Way, then we end up with a very different graph. Most of the AGB stars in the galaxy are old because the star formation history peaked about 10 gigayears ago. And what this means, the mass loss that we see from red supergiants and AGB stars in our galaxy today should be split about 20%, 80%. So most of the mass loss that we see is coming off these low mass AGB stars. And the AGB mass loss is split about 20% carbon rich and about 80% oxygen rich. And it's typically from stars of about 1 to 3 solar masses. These don't become the sort of extreme stars that the IRC 10216 poster child stars that we are used to observing in a lot of these galactic surveys of CO lines, CO emitting stars, all these OHIR stars, things like that. These are not representative of what is giving back material to the interstellar medium. What we can do is look at these individual stars, 1, 2, and 3 solar masses, and work out what the mass loss rates of these stars should be as they evolve over their lifetimes and lose their envelopes back into the interstellar medium. And what we find is that most of the mass loss from these stars is actually coming off at something times 10 to the minus 7 solar masses per year. In a lot of cases, it's a lot less than that, 10 to the minus 8 solar masses per year, or even less. That's true regardless of whether you're looking at the carbon stars or the S-type stars or the M-type stars. I'm comparing some numbers here to ACES paper back in 2015. I'm picking this because it's a really good summary of what the Swedish group has been doing in terms of surveying these CO lines around observations towards stars in the Milky Way, in particular the solar neighborhood. And I'm picking this one in particular because it's one of the least biased surveys out there. However, it's if you look at the M-type, the S-type, and the carbon stars that are observed by the survey, we've got 16, 6, and 16. Whereas if we look at how the stars are returning mass to the interstellar medium, you should actually split that survey up: 29 M-type stars, 2 S-type stars, and 7 carbon stars. Similarly, if you're looking at splitting up observations by mass loss rate, we really need more stars that are losing lower mass loss rates and fewer stars that are losing higher mass loss rates, if we want the sampling of stars to be proportional to the mass contribution back to the interstellar medium. And this problem becomes a lot worse if you want to look at things like what the typical AGB star is in terms of numerics, which is what we're doing when we're looking at these galaxies like the LMC and the SMC. We're looking at numbers of stars. And the problem is that if you want to look at a survey like this, you need 300 stars that are losing mass rates of less than 10 to the minus 8 solar masses per year for every star that's losing mass at 10 to the minus 6 solar masses per year or above. So we have this real observational bias towards high mass loss rate stars and carbon stars as well in existing stellar samples in the Milky Way. And this makes it really difficult to compare what we see in the Milky Way to what we see in these external galaxies. Now, there are new surveys coming along the line that are trying to address some of these issues and look at AGB stars in a statistical sense. Now, I've highlighted 3 of the main ones here: Termium, Death Star, and NESS. I'm involved in Termium and NESS myself, but Death Star I've included here because it really nicely fits the gap between them. Termium is looking at high-resolution, high-sensitivity observations of a small sample size of stars with ALMA. What we can do with this sample is look at what a typical AGB star is. We can look at how binary companions affect the AGB wind. We can look at dynamics of these winds in incredible detail and explore individual gas clumps and what their chemistry is doing, and how this is affecting the morphology of the wind, how we convert a spherical AGB star into a planetary nebula. At the opposite end, we've got the NESS survey, which is a tiered survey of about 800 stars. We are looking at virtually every star within 250 parsecs of the Sun, virtually every AGB star at least. And as we progress further out in the survey, we are looking at stars with progressively higher mass loss rates. So we're trying to sample volume complete samples of stars within the Milky Way using this process. This is single dish observations for the most part, and so it's looking at low resolution, low sensitivity observations, which are good for probing the statistical variation in the stars, looking at the mass loss rates, the expansion velocities, cold dust around the stars. But we have limited information on individual objects. And Death Star sits nicely in the middle. It's got a moderate sample size, it's got moderate resolution and sensitivity. And that allows it to look at the variation and things like envelope size and morphology and mass loss rates and expansion velocity in more detail for individual sources than NESS can, but with a larger statistical sample than Termium. So these 3 surveys can really work together to look at what a typical AGB star in the galaxy is and how individual AGB stars' properties can vary despite the fact that they may have very similar bulk properties. The problem we're facing with NESS is how do we get a homogeneous set of evolved star parameters? how do we get a set of stars in the first place, and how do we get their properties? We obviously want homogeneous observations, which we can accomplish, but we also want homogeneous extraction and fitting of data in the literature. From a reproducibility and manpower limited system, we want, therefore, something that's automated. We want an automated tool to extract these parameters from the literature. So we can get things like mass loss rate and expansion velocity from the CO spectra. There's things like pulsation properties that we can just look up from literature, and chemical types, and all these other kinds of parameters that we might need. But in terms of finding out dust production rates, stellar temperatures, luminosities, and maybe things like even mass or metallicity or evolutionary state if we can, then we really need to compute these homogeneously ourselves. A lot of these can come from things like spectra or PL diagrams, but a lot of these, particularly things like luminosity, have to come from SED fitting. So what NEST needs is an automated SED fitter that can collect photometry together, fit temperature and luminosity, extract dust production rates, match these to the NEST observations and to literature data like pulsation properties and other parameters. It just so happens that the EU have been paying me the last 3 years to actually come up with one of these automated SED fitters. Part of an Explore project that's got 7 space science apps. A lot of these are to do with galactic chemical evolution and extinction and things like that aren't so relevant to AGB stars. But this particular one that I've been looking at, I've entitled the Python Stellar Spectral Energy Distribution Toolkit. And I'll give you just a minute to look at the acronym for that. It's very memorable. We're pronouncing it PIST. What PIST does is, if it's given a star, then it will go away to Gaia and Simbad and look up that star and come back with the RA and the deck and the proper motion. And we'll take that proper motion, propagate it across a whole heap of different epochs, and go away to Vizier and look at photometry from those epochs and pull together a proper motion corrected spectral energy distribution. It'll then go away to other Vizier catalogs and pull back a heap of ancillary data, which will give us things like distance and metallicity if it's available, abundances if they're available, pulsation periods, etc. What this distance allows us to do is it refers us to a 3D extinction map, and that means we can extinction correct the photometry and put them on an absolute scale. We can fit a black body, which lets us do color correction to the photometry, and we can flag saturated data. We can perform outlier rejection. And then what we can do is we can convolve model atmosphere spectra with filters, the filters that's been observed with, and we can create a model fit to the spectrum. We can pull out of this effective temperature and luminosity of the star, and we can see in this case there's an extremely small infrared excess found. I've chosen this star for this particular reason because it's got that small infrared excess that's just on the limit of our ability to detect it. What we can do with this is pull up an HR diagram of AGB stars within 300 parsecs of the Sun. These are all the AGB stars we found. There's 487 of them above a luminosity of about 700 solar luminosities. Includes obviously RGB stars as well. And I've highlighted the NEST targets, which are circled. So you can see that NEST is actually taking on a lot of the AGB stars within 300 parsecs of the Sun and measuring the gas phase dynamics of them through CO observations. It still has problems with more extreme stars, and here we come up with philosophical questions like how do we define temperature when temperature varies with wavelength, and therefore how do we define the luminosity of a star? But the problem that we are facing the most is how far away are these stars? We don't have distances to a lot of these dust-enshrouded stars because they're too faint in the optical to get Gaia parallaxes, and we don't have other reliable methods of getting distances to them. So to summarize both sides of these observations, stars and other galaxies are hard to observe. They're too far away to get reliable measurements of in a lot of cases. Whereas stars in the Milky Way are hard to survey because it's difficult to pull together statistical samples. But if we want a holistic understanding of AGB stars, we need a synergy between these two different approaches. we need to be able to collect samples of A to B stars in the Milky Way and translate that knowledge down to stars and other galaxies. That means that we need to understand what typical A to B stars in the Milky Way are doing to compare to typical A to B stars in these other galaxies. We don't just want to be looking at the poster child cases. The problem is that existing Milky Way samples don't really reflect these typical AGB stars. They go out to the exciting stars, not the humdrum boring stars. And so we don't have numerically or by mass return reflective samples of AGB stars in the Milky Way. Particularly the low mass stars and low mass loss rate stars are undersampled and understudied. Conversely, for the higher mass loss rate stars, dust and shrouded stars, distances remain the dominant uncertainty, stopping us making progress with understanding these stars as a statistical cohort. We can see future prospects improving this. We'll get more distances from Gaia DF4 and 5, but we'll need distances to the optically faint stars as well, and those can only come from mesoparallaxes. We can expect improved photometry from things like Euclid and Roman and JWST for some of the external galaxies, but we're going to lack constraints still at the 25 to 450 micron range. Vera Rubin's going to come back with excellent time series. That's going to help us with pulsation periods. But one of the real problems is that we're not going to get information about binarity and how binary systems are affecting AGB stars. For that, we really need more high-resolution atomium-like observations to quantify how frequent binaries are, in particular planets that might be shaping the wind as well. And we want to see what the effects of these binary compounds and planets are on the wind, how they affect the morphology, how they affect the chemistry, how they affect the mass loss rates. And ultimately, what we want to do is match these high-resolution observations up to the infrared spectra and CO line profile morphologies we see of more distant stars in the Milky Way, and then match that onto these other galaxies. And only by doing that can we actually infer what's happening with AGB stars across the universe from the Milky Way to high redshift galaxies. And finally, I would like to end on an advertisement. I cannot join you tonight, unfortunately. I would love to be with you at something Melbourne's hospitality, but I hope that many of you take the opportunity to get iced tonight. The address is here. I can't join you, but if you are ever over in Manchester or up here in sunny Scotland, then please just drop me a line and I can help you get piced. And in fact, I will enjoy getting piced with you. Thank you very much for your attention. I'll now open the floor to questions.
Hi. Thanks a lot for the really nice talk. As someone potentially interested in using PICE, I was wondering if you could comment on how the uncertainties on the stellar parameters you get out from PICE are, I guess, computed, or how you'd quantify them.
Yes, so uncertainties are something that we really struggle with. And this is, we've effectively glossed over the uncertainties here. We've got representative uncertainties that we're giving. And there are scaling factors that you can use to apply these uncertainties to individual stars. However, the problem is that most of the uncertainties that we are looking at for these photometric surveys are woefully underestimated. That's because what you're looking at is the uncertainty in a particular observation, a particular detection. And that doesn't include anything like variability, errors in filter profiles, errors in photometric zero points, errors in disentangling crowded systems. There's a whole heap of uncertainties here that we cannot quantify. And so rather than attempt to quantify that in any kind of guesswork framework, what we've done is just benchmark the code against different systems and give a representative error for a well-fit SED. And therefore, as you get progressively worse fit as SEDs with less data or what have you, then those parameters, those uncertainties will increase with some semi-understandable factor.
Great, thank you.
Hi, Ian. Thanks for the nice talk. So how easy would it be to use PICE to also fit like spectroscopic data, from ISO or PAX or whatever?
Yeah, so at the moment we don't do things like extinction fitting. So we don't do dust modeling in PICE. But what we do is collate the SEDs that can then go into something like grams or beast or desk. These other tools that are designed specifically to do that. So it's not going as far as modeling the mass loss from the stars. It's just looking at the SEDs at this stage.
Great.
Does that answer your question?
Yeah, thanks.